to a new demonstration of GriidAI, an advanced geospatial platform designed to perform a wide range of GIS and remote sensing operations through simple, intuitive instructions. In this session, we will explore how GriidAI enables users to seamlessly work with vector and raster datasets. Here, we will be using building footprints, road networks, school locations, census, track boundaries, elevation models, as well as satellite imagery. This demonstration presents a series of widely used GIS tools, showcased individually to emphasize its specific purpose and functionality. Through these independent operations, GriidAI illustrates how geospatial tasks can be executed efficiently and at scale without reliance on complex scripting or manual intervention. So let's begin by creating a new session. Let's rename the session based on our current objective. Before starting the process, let's upload all the datasets which we are going to use in this demonstration. Great, all the data has been uploaded. We can check out the uploaded data into the data catalog. We can visualize some of the uploaded datasets before proceeding. This is the census tract data for the area of interest in our Miami region. Similarly, we can also check out the road network as well as the building footprints. So let's continue with our demonstration. We begin by reading the building footprint dataset, and let's examine its attribute table. The agent is processing, and the agent has provided us the key details regarding the features present inside the building footprint data. This step is fundamental in any geospatial workflow as it allows us to understand the structure of the data, including key fields such as unique identifiers, classification attributes, and other descriptive information. This result is a structured view of the dataset, helping us identify which attributes can be used for filtering, grouping, and further analysis. This step ensures that the data is well understood before applying any spatial operations. In real-world use cases, this is commonly used in urban planning, cadastral mapping, and asset management systems, along with any basic geospatial workflows where understanding attribute data is critical before analysis. Next, let's check out the split operation, which will divide the building dataset based upon the attribute field primary OCC. The resultant of this process will be multiple output layers representing the top 10 specific categories of buildings based upon the primary OCC. This process will generate categorized datasets that can be analyzed independently based upon their primary classes. This process of splitting allows us to isolate specific types of buildings where we can do a further focused analysis. This type of tools are widely used in applications like zoning analysis, land use planning, and policy-based classification workflows. Great, the process is completed and the data catalog is reflecting the updated files based upon the different primary occupancy classes. Let's check out some of them on the map. Next, we move on to the next operation. We will check out the append tool that is used to recombine selected subsets into a single dataset. We will be appending the primary occupancy classes for multifamily and single family to create a residential occupancy class building dataset. Unlike merging, the append tool adds records into an existing dataset while maintaining schema consistency. The result is a unified dataset that aggregates the selected features. This tool is useful for combining datasets that share the same structure. Great, the results have been generated and the data catalog is reflecting the updated file accordingly. Let's check out the attribute table to validate the results. As you can see, there is primary occupancy for both multifamily dwelling as well as single-family dwelling present into the attribute table, and the both files have been combined. We can also check out the results on the map. As you can see, both the single-family dwelling and multifamily dwelling have been appended and been created as a single file. This append tool in the real world can be used for the data integration workflows, such as updating GIS databases with new survey data or combining multiple datasets into a centralized repository. Now let's move on to other vector operations. We will start by a buffer tool. We now create a buffer around the road network, generating a zone of influence around each road segment. A buffer essentially expands a feature outward by a specific distance. Here we are using a 3-meter distance, creating a polygon that represents the proximity. The result is a continuous zone that highlights areas close to these roads. Great, the results have been generated, and the data catalog also reflects the updated buffer file. Let's check it out. Onto the map. Firstly, let's visualize the road network layer, and then we will overlay the buffer layer on top of it to validate the results. As you can see, the buffer of 3 meters has been correctly generated on each of the road segments. This tool helps in identifying the areas easily accessible via these transportation networks. Also, this is commonly used for transportation, planning, accessibility studies, even for environmental impact assessments and infrastructure development. Now let us look at one of the applications of this buffer tool. Using this buffered road layer, we will use this on a terrain raster to mask that. Here, using this buffered road layer, we are applying a mask operation on the DEM raster. This masking operation restricts the raster to only those areas that fall within a given geometry, setting all other areas to no data. The result of this operation will be a filtered raster showing elevation values only along the road corridors, or to be specific, the road buffer. Great, the process is completed. Let's check out on the map the generated results. As you can see, the only DEM pixels which are falling inside the road buffer have been retained, and masked out, the remaining portion is set to no data. This type of analysis is very useful in applications like road design, slope analysis, and corridor-based environmental assessments. Now let's move on to the next tool. We will check out the vector clip tool. For that, we will be using a Miami census tract dataset along with the building footprint data. So first, let's visualize the Miami-based census, tract data, and its attributes. Let's see all the census tracts available within the region of interest. We can also select a few of them. All these census tracts have a unique NRI ID to identify them independently. Let's start our clip operation. This clipping operation extracts only the portion of the building dataset from the selected census tract for the Miami County. The result is a subset of building footprints confined to a single administrative unit. Great, the results have been generated. Let's check them out on the map. As you can see, the buildings residing only in this particular census tract have been clipped. This tool is used extensively in urban governance, demographic studies, and municipal planning, as it enables localized analysis within defined geographic boundaries. Now let's move on and look for different tools using vector datasets. One of them is Select by Location. Here, before directly jumping onto the tool of Select by Location, we have asked the agent to create a buffer around the school locations representing their area of influence. Then, eventually using the tool of Select by Location, we will identify the buildings which fall within this buffer. Unlike clipping, this operation does not modify the building's geometry, it simply highlights the selected features lying within the region of influence. Great! The analysis is completed. As per the agent, there are total 280 school points which were buffered by a distance of 500 meters. Out of that, there are total 102,000 buildings ranging within the 500-meter distance and more, then 200,000 buildings which are far from it. The agent has created a new column, with the flagging of true or false whether the building is lying within the 500-meter distance near the schools. Let's check out the building footprint attribute table. As you can see, this new column is created and it is populated based upon true or false based upon its distance from the nearest school. Let's move on and check out the next tool that is point in, polygon. For this, we will be using two datasets again, that is the school POIS and the census tract data. Before jumping on to the demonstration of the tool, let's visualize these datasets on the map. As you can see, the red points are nothing but the school POIS, and these blue polygons are the NRI census tract. Now, based upon the point in polygon analysis we perform, we will identify which school points fall in which census tract and then generate a result as a table. That summarizes the number of schools within each administrative unit. The output of this analysis will be a table having the corresponding NRI ID and the associated school count for each of the NRI ID polygons. Great, the results have been generated and a new CSV file has been created. Let's view the table. As you can see, the spatial association between different datasets have been converted into a measurable statistics. This type of applications or tools are used in different types of studies like facility distribution analysis, resource allocation, and even infrastructure planning. Now let's look at some of the more complex GIS tools used for analysis like intersect and spatial join. We will now buffer the building footprints and perform a spatial join with the road network. This operation establishes a relationship between buildings and nearby roads, generating a mapping table linking the unique fields, that is building ID for building, footprints, and road identifiers. This particular operation will serve as a database that will identify which roads will serve specific buildings. Great, the process is completed. The agent was successfully able to create a 50-meter buffer around each building footprint, and it performed a spatial join between the building buffer and the road network, and has created a mapping table to map each individual build ID and its corresponding linear ID. It has also validated the results to provide us unique counts for each of these categories. As we can see, there are total building ID, linear ID pairs as 688,000 and unique building. Match pairs greater than one road segment are close to 300,000. Let's check out the table which has been mapped. Great. Now let's look at the erase operation or the erase tool. This tool is specifically used to erase or delete some of the geometries from the existing dataset. Let's take one example to showcase these results. We are using the erase operation to remove building footprints that fall within the distance of 100 meters from the coastline. The result is a dataset where features in restricted or high-risk areas near to the coastal regions will be excluded. Great, the operation is completed, and as per the agent, there are close to 11,000 buildings which were within the range of 100 meters from the coastlines, and that have been removed. We can even visualize the results on the map. For visualizing, let's first switch on the original building footprint layer as well as the coastline layer to see what all buildings were present within that range. Great. Now we will switch on the erased building footprint layer to compare. As you can see, the top layer, some of the buildings which are within the range of 100 meters have been successfully erased or deleted, which helps us validate that the operation done by the agent is completed correctly. Now let's move on and we will do a bit more complex task involving the near distance analysis. We have prompted the agent and asked it to use the same two input datasets, that is the building and the coastline data. We will calculate the distance of each building from the coastline. This is called near analysis in terms of geospatial data. Here we have asked the agent to store the results for the distance as a new column in the same attribute table of the building data. These calculated distance values will help us quantify the spatial relationships between the coastline and the buildings. Great. The analysis is completed and the agent has also provided us the statistics. A new file with an additional column of distance coast in meters is created, and the maximum distance is close to 18,900 meters, and the mean distance of buildings is close to 6,000 meters. Let's open the attribute table to view the results. As you can see, a new column is created showcasing the distance from each of these building footprints towards the coast. This type of analysis is usually used in risk assessment, insurance modeling, and even urban development projects near the coastlines. Now let's move on to see some of the raster operations. Now we will see raster clipping based upon a polygon extent. We will ask the agent to clip the DEM raster based upon the NRI ID of the census tract. This type of operation is usually done to reduce the larger dataset to a smaller scale, manageable area, and improving performance as well as focus. This clipping operation ensures efficient processing as well as localized analysis. Great, the results have been generated. So for validating the results, first let's visualize the input layer for comparison purposes. This is the full DEM data for the whole region that we have used for the study. Now let's check out the clipped region. As you can see, a smaller portion based upon the census tract, NRI ID, has been successfully used to clip this data. This type of clipping operation is essentially useful for projects such as terrain analysis and localized environmental studies. Now, let's look at some of the raster calculation tools used to calculate different types of analysis based upon satellite data. Sentinel-2 be specific. We will calculate normalized difference vegetation index, NDVI, using this raster calculator tool. NDVI is calculated using red and near-infrared bands. This index highlights the vegetation health and also tells where high values of vegetation signify good vegetation. This index also helps distinguish vegetation from non-vegetation areas. It is specifically used in case studies like agriculture, forestry, and environmental monitoring. Great! The results have been generated. Let's visualize them on the map. As you can see, the NDVI raster has been successfully created, which has used the Sentinel-2 data bands number 8 and 4, which are NIR and red to be specific. It is the normalized difference of these two bands. Now let's check out other raster operations. We will ask the agent to create a false color composite by combining the bands from the same Sentinel-2 data like NIR, red, and green. The basic purpose for the FCC is to enhance the vegetation visibility, making it easier to interpret to identify different land cover patterns. Great, the false color composite has been created successfully. Let's check it out on the map. As you can see, vegetation appears here prominently in red color, enabling for a quick analysis. This type of tool is especially used in plethora of remote sensing applications like land cover and land use cover mapping, and also used for different types of satellite image interpretation techniques. Now let's look for another tool, that is raster reclassification. We can use the newly created NDVI raster itself and ask the agent to reclassify it into meaningful categories such as water, built-up areas, and vegetation. We have asked the agent to generate relevant classes based upon the real-world scenario to classify the data into different datasets. We can briefly view the plan to see the thresholds for each of the class and grant a permission to the agent for proceeding. This classification of the continuous data simplifies it and makes it more easy to interpret into different classes. Great! The reclassification process is completed. Let's visualize the new raster. As per the agent, there are 4 classes. Class 1 represents water, Class 2 represents the built-up or habitation in the gray area, 3 is the sparse vegetation, and 4th one is the dense vegetation. This type of analysis is usually useful for land use, land cover classification, as well as environmental zoning. Now let's move on to a bit more complex raster vector combined analysis. We will do the zonal statistics. We will ask the agent to calculate the mean elevation for each building footprint. For this, we have the building footprint as well as the DEM data. Great, the results are finally generated. The agent is saying that there is a discrepancy in the values of elevation, but that is fine as the DEM raster is having the units of millimeters and not meters. So, let's check out the attribute table information to see whether the table is populated correctly. As you can see, the mean elevation table is correctly generated and showing accurate values. This type of tool integrates the raster values into the vector features. This tool is especially useful for flood modeling, terrain analysis, and even for infrastructure planning. Now let's look at the last part, that is raster to vector conversion part. Let's ask the agent to rasterize the building footprints. This rasterization of building is a classic vector to raster conversions. We have asked the agent to rasterize the buildings, and each pixel lying inside a corresponding building will have a pixel value as the building ID, which is the unique identifier. This vector to raster conversion enables grid-based analysis. In real-world use case, it is used in large-scale simulations and spatial modeling. Great! The rasterization process is completed. Let's visualize the rasterized version of buildings on the map. For comparison, we will also switch on the building footprint vector layer. As you can see, the buildings have been correctly rasterized to their corresponding geometries and even have the accurate build IDs. With this tool demonstration, we have come to an end to this demonstration. This video showcases how GriidAI simplifies complex workflows into intuitive operations, from data exploration to advanced spatial analysis and raster processing. GriidAI enables users to perform powerful GIS tasks efficiently and at scale. By eliminating the need for complex scripting and integrating multiple data types into a unified workflow, GriidAI empowers users to transform spatial data into meaningful insights with speed and precision.